All right, we turn to chapter 25, the driving forces of weather. All right, so these are some of the things that we're going to talk about. We'll start with atmospheric moisture, then get into the different variables for the weather, mostly temperature and pressure um, and humidity. And then we'll talk about cloud development, air masses, fronts, storms, violent weather, and then weather forecasting. Okay, all right, so there are four factors that influence the weather. One, of course, is atmospheric moisture. We're going to spend a little time talking about that. Um, the general thing there is what we consider, what we call the relative humidity. All right, we'll get to that in just a little bit. The temperature, of course, the temperatures we'll be in Celsius, but there's always there's an easy conversion between Celsius and Fahrenheit. There's the air pressure that of course goes down as you get higher and higher, and of course the arrangement of land and water features. Like if you're if you're over the open ocean versus in a bay where this or you're approaching a mountain or something like that's going to affect the weather. Or approaching the mountain or the other side of the mountain, we'll learn about rain shadows and stuff like that. All right, so atmospheric moisture and water vapor. Okay, so the temperature. So this is some physics here. Temperature is a measurement of the average kinetic energy of molecules. How quickly the molecules of air are moving around. All right. So high temperature, the air and water molecules are moving fast enough that the energy these things will bounce off of each other and remain in a liquid state. If it's already a liquid, let's say, so you already have liquid, and if the water molecules are in the vapor state, then it's of course if there's enough energy in the liquid state, some of the water molecules can escape and become evaporated and basically become part of the air. Part of the. I mean, it's still water, of course, but it's water in a vapor state. All right, so or in a gaseous state. With an increase in temperatures, there's always an increase in evaporation, and you get more water in the air. And that's actually a really big deal when we start talking about relative humidity. Warmer air can hold more water. Air with a lot of water is considered very humid. Like I said, we'll do the exact the equation that describes that. What's going to be called relative humidity. It's actually a big deal whether it's what we call relative humidity. All right, and that's basically what they talk about when they talk about the humidity. When the news talks about what the weather is, they might just say the humidity, but they really mean the relative humidity. All right. Let's see. When the temperature cools, the water vapor molecules can slow down, and they can remain in the vapor state, and they begin to clump together. So you need some cooling to take place, and then you can have what's called condensation. All right. So condensation, of course, depends on the temperature. The water vapor can condense to form. It usually forms clouds first, or if it's on the ground, if it's right at the ground, it'll form dew or fog. If it's in the air, it'll form, like I just said, it forms clouds. If it depends on the saturation of the air, you can actually begin to form water droplets, and if they get big enough, that it'll actually rain. Not the rain doesn't always hit the ground, as we're going to find out. It depends on what the evaporation rate versus the condensation rate is as the water droplet falls. So if it's cold enough, then the rain, of course, will be snow or ice or even frost. And in fact, in most precipitation, when there's actually something falling from the sky, it actually falls as frozen precipitation, and then and that usually, not always, but usually, and then when it gets closer to the ground, if it's cold, if it's warm enough, closer to the ground, which usually is a little bit warmer, sometimes a lot warmer, the snow or freezing rain will melt, and we'll have rain, just good old fashioned rain. All right. No matter how dry the air may feel, there's always a certain amount of water vapor in the air, and there can be tremendous amounts of water vapor in the air, and there are times when we feel that, when we talk about the air feels very muggy. When it feels muggy, that means the relative humidity is really high. Humidity is the mass of water vapor in a given amount of air. And when we talk about a given amount of air, we're going to start talking about what's called a parcel, which I mentioned a little bit before, but I just want to describe that again. And that's you're not talking about a continent amount, like the air over a continent. It would be like a parcel would be maybe the air over a small town or a city or a lake or something like that. That would be a parcel of air. It's not like a defined. It's not a well-defined amount. It's just a relatively kind of a local amount of air. That's a good way to think of it. See, the humidity the humidity that's in the air talks about how much water vapor there is. When the air is saturated, we're at maximum humidity. The air is at maximum humidity, and then you can have condensation occurring. That's in fact when clouds form or when there's fog. And if it keeps going, you eventually can get to the point where it's raining. It's actually precipitating from the air. All right. Let's see. So this is saturation occurs when the air's temperature drops, and it causes the water vapor to condense. So let's see, and the temperature at which the saturation occurs is called the dew point. Right? That's actually really critical. We have a lab that where you measure the dew point. The lab works okay. I mean, it's not. We don't have the best equipment for that. Hopefully someday I'll change that. But anyhow, so that's the important part is when it's completely saturated. You find the dew point, and the dew point is usually, if it's not raining or something like that, the dew point is usually less than it has to be either equal to or less than the air temperature. It's never greater. All right. So when the air is saturated, the maximum humidity has been reached, and that's what's called the water vapor capacity. All right. We're going to measure that it's measured in units called like grams of water vapor per kilogram of air. All right. So saturation and water vapor capacity are temperature dependent. That's really important. There's some tables that we're going to look at. There's actually a graph but the graph is very nonlinear, and so it's sometimes it's hard to get the data off the graph, as you'll see. Air capacity for water vapor varies with temperature. That's important. Warm air can accommodate more water vapor than cold air. That's a really important point right there, right? Warm air can accommodate more water vapor than cold air. So higher temperature means more energetic water vapor molecules. You get more evaporation going on. Increasing temperature, increase in water vapor capacity. As the air cools, it accommodates less water vapor. And cooler temperature means slower moving water vapor molecules. Condensation is the rule. And you have this decrease in temperature, decrease in water capacity. All right, so here is our relative humidity formula. So notice this thing called relative, well, that should be an equal sign right there. The relative humidity is equal to the water vapor content, the humidity divided by the capacity, the water vapor capacity. And what happens is you have to look this up on a table. Like I said, there's a graph. It's kind of hard to read. I mean, you can, eventually you can. You'll see the graph in just a second. It's kind of a pain to look at the graph. Or to get any information from the graph, I should say. It's much easier to just look at the tables. You see what the temperature is, and you can read off what the water capacity is. So the relative humidity depends on the actual water vapor content and the air temperature. All right, so that fraction is multiplied by 100 to give us the percent humidity. All right, so here, see, this is the graph, or this is, yeah, kind of the graph. So when let's start in the middle here, or not in the middle, in this curve right here. When evaporation rate is exactly equal to the condensation rate, you follow. That's you have the maximum saturation. All right, so. Notice it varies with temperature. Okay, that's the point, and that's it. Like, for example, let's say it's 10 degrees. Okay, so you go up until you reach this curve, and then you have to guess. That this one's pretty close to being a maximum. The maximum, what's called the specific humidity, would be in. It looks like it's roughly 10 grams per. So it's grams of water vapor per kilogram of air. All right, so that's the way it works. All right, let me just read this real quick before this video ends. In saturated air, condensation and evaporation are in equilibrium. All right, so that's this line that I just mentioned. If the condensation rate is greater than the evaporation rate, you're up here. If the evaporation rate is greater than the condensation rate, you're down here. All right, so evaporation rate depends on that. The condensation rate depends on the humidity and the temperature. When evaporation rate is equal to the condensation rate, the relative humidity is 100%. When the evaporation exceeds the condensation, the air is no longer saturated, and the relative humidity is less than 100%. If the condensation rate exceeds the evaporation rate, the air is supersaturated, and so you're going to begin to get water droplets that form. Okay, that doesn't mean they're going to fall as rain. There's other conditions as well that go into it, but you'll start to form water droplets. They've got to accumulate. As we're going to see, that you got to get a whole bunch of them together before they begin to fall, and they're being pushed up by the air, basically, and then they got to get heavy enough to fall. All right, so we'll address that in the next video. Okay, so